Hello, I want to start today by trying to give you a little bit more information on something that will be useful for the homework assignment. And specifically, I want to talk about atmospheric stability. And we have three different definitions for stability. And the first is a stable atmosphere. And in a stable atmosphere, an object that is displaced will return to its original location. An unstable atmosphere, an object that is displaced will accelerate away from its original location, no matter how small the perturbation. And in a neutral atmosphere, an object that's displaced will remain in its new position when the displacement force ceases. And I'll give you an example of those now. So here we have a marble in a basin, and we're going to give that marble a nudge, and then we're going to see what happens. So as you can see, the marble returned to its original location despite the fact that it was given an initial perturbation, and that is the definition of stable. Here we have a slightly different situation. We're going to nudge our marble and see what happens. So in this particular case, a small nudge of the marble made it accelerate away from its current condition, its initial location, and that's going to be the definition of unstable. Here we're going to move the marble horizontally and then stop it and then see what happens. So in this situation, the marble remained where it was when the forcing stopped, and that is, by definition, a neutral situation. So the previous three examples were all essentially horizontal with the marble. In the atmosphere, if you take all of those and flip those into the vertical, you'll have the behavior of an air parcel. So the one thing that we need to do to measure the stability of the atmosphere is to determine the environmental lapse rate. And the environmental lapse rate is defined as a change in temperature divided by a change in height. So how does the temperature of a dry air parcel change when it's lifted? So here we have temperature on the x-axis and altitude on the y-axis. We have an air parcel, which I'm grabbing, which is at the surface, and it's initially 20 degrees Celsius. And we're going to lift that air parcel, and that air parcel is not going to mix with the environment, and it's just going to expand as the pressure decreases. And as it expands, the temperature will decrease. And by the time that air parcel reaches 1 kilometer, its temperature has decreased 10 degrees Celsius. And then we can define that lapse rate, or that change in temperature, as the dry adiabatic lapse rate, and that happens to be minus 10 degrees Celsius per kilometer. So what is this mysterious dry adiabatic lapse rate? Well, it just refers to a dry air parcel that has a relative humidity of less than 100%, and it's adiabatic, which means that there's no exchange of mass or energy with the environment. So this air parcel remains isolated from the environment during its ascent. And as long as those two conditions are met, then the air parcel will always decrease at a rate of 10 degrees Celsius per kilometer if it's lifted upward. What happens if we push this air parcel downward? Well, it turns out that the process is reversible as long as the air parcel does not have any cloud or liquid droplets in it. And as we push that air parcel down, it's going to move to an area of higher pressure, which is going to compress it, which is going to warm it back up the exact same amount that it cooled during the ascent. And its final temperature is going to be the same as its initial temperature at the ground at 20 degrees C. And once again, it's following that dry adiabatic lapse rate. In this case, it's positive 10 degrees C per kilometer because the air parcel is descending. So, since the only thing we need to know to determine the stability of the atmosphere is the environmental lapse rate. Let's look at how we measure the environmental lapse rate and the impact that it has on stability. So to measure the atmospheric lapse rate, we need to launch a Ray-Winson balloon. This balloon will have a temperature sensor, a humidity sensor, pressure sensor, and an ability to measure the horizontal winds. And so let's just say that we go out and we launch this balloon, and the temperature at the surface was 20 degrees C, and we launch our balloon and it rises up through the atmosphere, and the temperature remains constant with height. We refer to this as an isothermal situation, a constant temperature with height. That's the environment. Now we're going to do a thought experiment with our air parcel. So we're going to grab our air parcel at the surface, which has the same environmental conditions as the surface, so it's going to be 20 degrees C, and then we're going to lift that air parcel, and as we lift that air parcel, it's going to follow the dry adiabatic lapse rate because it's not going to mix with the environment. And this time we lifted the air parcel 2 kilometers, and since the dry adiabatic lapse rate is minus 10 degrees Celsius per kilometer, if we lift the air parcel 2 kilometers, then its temperature is going to drop by 20 degrees, and its temperature at 2 kilometers is going to be 0 degrees Celsius, which is much colder than the environment at that level. So is the air parcel colder or warmer than the environment after it's been lifted? Colder. Is this air parcel going to be more or less dense than the environment? Well, since they happen to be at the same pressure, the density is primarily controlled by the temperature. And so the colder air parcel, the molecules will be closer together, and you can pack more mass into a smaller volume, so it's going to have a higher density. So the air parcel is more dense than its surroundings. If it's more dense than its surroundings, will this air parcel rise, sink, or remain stationary? Well, buoyancy is controlled by density differences, and things that are more dense than their surroundings will sink, and things that are less dense than their surroundings will rise. So in this case, this cold air parcel will sink. Is this a definition of stable, unstable, or neutral? Well, since we lifted the air parcel, we forced it upward and then let go, it's always going to be colder than the environment, which means that it's going to be more dense, which means that it will sink back down to the surface, and that will be the definition of a stable environment. Let's take another example. This time we launch our Ray-Winson balloon, and the temperature decreases by 10 degrees Celsius over 2 kilometers. So the environmental lapse rate was minus 5 degrees Celsius per kilometer. And we repeat our thought experiment with our air parcel. The air parcel behaves exactly the same as it did before, because it's following the dry adiabatic lapse rate. And let's go through those thought experiment questions again. Is it colder than the environment? Yes. Is it more dense than the environment? Yes. Will it rise, sink, or remain stationary? Well, it's going to sink. And that's going to be stable. Case number 3. We launch our Ray-Winson balloon, and it just happens to measure an environmental lapse rate of minus 10 degrees Celsius per kilometer. So we take our air parcel and do our thought experiment again. How does the temperature of our air parcel compare to the environment? Well, it's exactly the same. How is that going to affect the density? It's going to be the same. Is it going to want to rise, sink, or remain stationary? Well, there's no buoyancy involved because it has the same density as the environment, so it's going to remain stationary. And by definition, that's going to be a neutral situation. And the only thing that's changed in all of these is the environmental lapse rate. We launch our balloon yet on a different day, and the temperature is decreasing very quickly with height. Let's repeat our thought experiment. We lift our air parcel. Something's different now. The air parcel is now warmer than the environment at 2 kilometers. Is that going to make it more or less dense? Well, it's going to be less dense than the environment now. which means it's going to want to rise because it's more buoyant than the surroundings. Is it unstable, stable, or neutral? That's going to be unstable. Any small perturbation, any slight nudge upward of this air parcel, and it will become warmer than the environment, which means that it's going to spontaneously rise. And here we have the atmospheric stability for the case number 5, where we have a temperature inversion. So now the temperature is actually increasing with height. We do our last thought experiment. We lift our air parcel. Its temperature is now 0 degrees Celsius. Our environmental temperature is much, much warmer than that. So there's a very strong restoring force on our air parcel. Our air parcel is much colder than the environment. It's much more dense than the environment. It's going to sink, and it's going to be very stable. So in this situation, any pollution that is emitted near the surface, there is a strong environmental restoring force that will try and ensure that that pollution stays near the surface as well, which is why we have poor air quality conditions during the inversions and the cold air pools. Now that we have some better understanding of material that you need for the homework assignment, I'd like to return to our criteria air pollutants and look at the trends in those criteria air pollutants over time. So we're now up to ozone. So ozone, the standard for ozone has changed over the years. Initially, it was a 0.12 parts per million 1 hour standard, but that was changed in 2005. It was actually revoked. Prior to that, we established the EPA established 8-hour standards. Based upon the science in the mid-1990s, it was determined that 0.08 parts per million would be the threshold for harmful levels for human health. Later on, in the mid-2000s, additional research showed that the ozone was actually more harmful at lower concentrations than previously thought, and they lowered the standard to 0.75 parts per million. And research continued, and by 2015, they lowered the standard yet again to 0.07 parts per million, which is equivalent to 70 parts per billion, and that's an 8-hour standard. If we look at the 8-hour ozone non-attainment areas for the 2008 standard, you'll see that most of California, at least the Central Valley of California, the Bay Area, and the Southern California are all in non-attainment areas for ozone. We also have urban areas like Phoenix, Denver, Dallas-Fort Worth, Houston, St. Louis, Chicago, Pittsburgh, Philadelphia, etc. are all in non-attainment for ozone. So in order to form ozone, recall that we need 3 ingredients. We need nitrogen oxides, which come out of the tailpipes of cars and out the smokestacks of combustion facilities and out of our houses if we happen to have water heaters and furnaces that are using natural gas. And then it also requires volatile organic compounds, VOCs. Those VOCs can be either natural or anthropogenic. Natural sources are many trees and bushes, are natural sources of VOCs. And then there's also the anthropogenic ones, which are associated with fuels, fossil fuels, and specifically refining and fueling of vehicles are common sources of VOCs, as are paints and some industrial processes. In Utah, we were determined to be in compliance with the ozone standards starting in 1997. And since then, we have 2 counties that are under a maintenance status, and that happens to be Salt Lake and Davis, where they're concerned about the ozone concentrations rising, and they just want to make sure that we don't violate the standards again. Let's take a look at the ozone trends. This is from 1980 to 2010. And during that time period, the ozone concentrations nationally were very slowly going down. And by 2008, about 50% of the stations in the United States were in violation and 50% were in compliance. And here in Salt Lake City, it's been very much bouncing around the national standard without much of a trend. There was a study that was done here in Salt Lake City back in the early 2000s that was looking at what fraction of the ozone during the summer events that we have here is due to natural background ozone concentrations, how much is transported in from other locations, such as California or Arizona or Nevada, and how much is generated from local emissions. And what they found is that about half of all of the ozone that we have here in the summertime is naturally occurring background ozone. Remember, we have the ingredients for ozone production. We have the nitrogen oxides, we have the volatile organic compounds. We also need sunlight, and all of the chemical reactions are temperature dependent. So if you have higher temperature, the reaction rates that create ozone are enhanced. And so at high elevation, you have lots of sunlight. During the summertime here in Salt Lake City, we have high temperatures. That's a recipe for creation of ozone. So half of our ozone is from background natural concentrations, and about a quarter is from anthropogenic transport from outside of our state, and about a quarter is from local sources of emissions. Let's take a look at sulfur dioxide. So the 24-hour standard for sulfur dioxide is 0.14 parts per million. And back in 2010, there were 4 areas in the United States, actually 6 areas, but 4 areas in the western United States that were in non-attainment for sulfur dioxide. And at the time, that was Salt Lake County and Tooele counties in northern Utah. There was a county down in Arizona and 2 up in Montana. What did all of those locations in the western U.S. have in common? They all had metal smelters associated with them. Metal smelters are a big source of sulfur dioxide gas to the atmosphere. As of 2017, the Utah and Montana non-attainment areas have gone away. They've gone into maintenance status. The one in Arizona is still there. And now we have a whole bunch of smaller urban areas and non-urban areas in the eastern part of the United States, which are in non-attainment. Some of these are associated with coal-fired power plants. Some of these are associated with refining of fuels, so oil refineries. So let's take a look at the sulfur dioxide trends. The trends are going down. Air quality is improving nationally. Nationally, it's well below the national standard for at least the annual arithmetic average. And in Salt Lake City, you'll see that it's been pretty flat after higher concentrations in the early 1990s had us out of compliance. So let's take a look. I was able to find data back to the mid-1970s. And Magna in pink is a city that's located right over near the northern part of the Ochre Mountains, close to this metal smelter that's over there. And Salt Lake City is in blue. And you'll see that back in the 1970s, the sulfur dioxide concentrations were very high. And then they quickly came down, and then they collapsed to very low concentrations starting in the mid-1990s. So why is that the case? Well, the Kennecott Copper Corporation voluntarily upgraded their smelting facilities in 1995 to reduce the sulfur emissions by 95%. Their new scrubbing technology removes 99.9% of the sulfur dioxide from the smokestack before it is released into the environment. This was quite a substantial investment of about $1 billion into the technology to clean the effluent. Let's take a look at the efficiency of the smelters and the air pollution equipment that removes the sulfur dioxide from the gas stream. Well, you'll see that according to the source, the Kennecott Copper Corporation smelter at 99.9% efficiency is the most efficient smelter in the world in terms of removing the sulfur dioxide gas. So what are the big sources of sulfur dioxide in Utah? Well, the first 4 of these actually are currently operating coal-fired power plants. Remember that sulfur is an impurity in coal, and when you burn the coal, it's oxidized and can come out of the stack of sulfur dioxide if it's not completely scrubbed from the smokestack. The 5th one here is a power plant that Kennecott Copper was using, and that power plant has now been shut down, and they invested heavily in renewable energy. They invested in wind power in Wyoming and solar power in Utah. So they replaced essentially the locally generated power with power that was being generated elsewhere in the region. And then we have the Kennecott Utah Copper Corporation smelter and refinery. Even though it's 99.9% effective at removing the sulfur dioxide, it still emits almost 1,000 tons of sulfur dioxide into the atmosphere per year. And then after that, you have a couple of local refineries. Tesoro and Chevron and Flying J just are some of those. Which ones are located in our valley? Well, there we are with the stars. Although, like I said, the Kennecott Copper Corporation power plant has been shut down. And so now the largest source of sulfur dioxide in the metropolitan area is the smelter and refinery operations, followed very closely by the Tesoro Salt Lake refinery. So let's do a summary of air quality in Salt Lake City. So of the criteria air pollutants, carbon monoxide, nitrogen oxides, lead, and sulfur dioxide are not currently a problem. They're well below the the National Ambient Air Quality Standards. Currently in non-attainment for PM 2.5. That's a 24-hour average PM 2.5 concentrations. That PM 2.5 is known to be hazardous to your human health. We've already talked about the impacts that it has on your lungs, the impacts that it has on your cardiovascular system, the impact that it has on causing strokes. It also has implications for preterm babies and gastrointestinal problems as well. So things that are likely to be a problem soon, PM10, which are the coarse particles, the larger particles around here. The biggest sources of PM10 are going to be blowing dust. And as the Great Salt Lake continues to recede due to drought and water diversion, we'll have more and more dust coming off of the lake bed locally, but there are other lake beds within the Intermountain West that are also undergoing the same type of desiccation, which will lead to more dust, which will lead to more PM10. And then we'll also have an ozone issue that's likely to be here soon. As the population of Utah has gone up, urban sprawl has increased the number of vehicle miles that people are driving, which is creating more VOC emissions and more NOx emissions, which is leading to higher ozone concentrations. We also are having a lot of ozone being transported in from places like California. So what are these pressures on our local air quality? The biggest pressure comes from population growth and urban sprawl. So more people need more places to live, more vehicle miles are driven, and if they live further from where they are actually working, then it exacerbates the problem. It also has the need for more gasoline, which requires more refinery output, which puts more VOCs into the atmosphere, and needs more electricity, which requires more either coal-fired power plants or renewable energy along the way. So this population growth pressure on local air quality can actually be circumvented if we were to switch to electric vehicles. Electric vehicles would have a very significant local impact on our air quality because much of our pollution is caused locally, especially during the winter time. Our winter pollution problem is primarily PM 2.5, and that the biggest component of the PM 2.5 is actually ammonium nitrate, which is a secondary particle that results from chemical transformations of nitrogen oxides. And those nitrogen oxides are primarily coming from vehicles, 50%, and industrial processes and people's homes. We also have some industrial expansion in the valley. You might have heard about the inland port, which is being built west of the airport. That is going to dramatically increase the amount of diesel trucks and trains that are moving through the area, and that's going to have an impact on local air quality as well. As are forest fires. Last summer, California had massive fires, and the smoke from those fires was impacting Utah and Salt Lake City very dramatically. And we've had local fires which have also impacted our air quality. And then we have the aforementioned windblown dust. And then I hate to say this, but fireworks, I've never seen any place in the country that loves fireworks more than Utah. And not only on July 4th, but on the Pioneer Day and July 24th, you'll see firework displays that are really amazing, but they're also really bad for air quality because of the metals that are in the smoke. And they don't contribute much to mass, but they're actually quite dangerous. I've often been called the Grinch that tries to steal the 4th of July. And I don't really want to steal the 4th of July, but I do have concerns about the air quality associated with the firework displays. So here we have a plot showing the number of vehicle miles traveled in Salt Lake County from the late 1960s all the way through the early 2010s. And there's been a pretty dramatic increase in the number of miles that have been driven due to the increasing population and the increasing urban sprawl. And how might we reduce our air pollution? Well, we can drive less, drive smart, use zero emission or partial zero emission vehicles. Those zero emission vehicles, the fully electrics, like I said before, would make a very big difference in our air quality during the winter time. Or we can also increase fuel economy because we burn less fuel, we put less emissions into the atmosphere. We can increase the use of mass transit or carpooling to reduce those vehicle miles that have been driven. And we can require new air permits to use the best available control technologies. And we can continue our inspection and maintenance program for our vehicles. So there was a study that was done in California. We've all seen these cars that are driving down the highway that are smoking. They're not being maintained well. There's a mechanical problem with the car. It's burning oil, something, and it's smoking. And California determined that just one smoking car puts out more pollution than 10,000 cars that are well maintained. And so the idea is behind this smog check program is to try and identify those few cars that are causing problems so that they can be fixed or taken off the road. And that would have a dramatic impact on the air quality by reducing those smoking vehicles. And I want to leave you with this thought. And just remember, we're all swimming in the same stuff. So do your part to spare the air.